Hi, so now we're starting material after that will not be on the first test. So the first thing I want to introduce now is a totally new type of component. We've worked with resistors and batteries so far. Now I'm going to introduce something called a capacitor. Capacitors are found everywhere. We're going to learn about how they're used, what they're used for a bit later. But let me just point out that if you open a lot of electric machine, you'll see things like this. Those are capacitors. They're fairly small, or you might see something like this. By the way, in the lab, our capacitors will look a lot like the one you see on your right. Sometimes you even have this form of capacitor where you can actually rotate. What you have here is really a set of parallel plates, and you can rotate them so that they partially overlap or completely overlap. Uh, you'll see why that's a capacitor and how it works very shortly. But I wanted to point out that they look like, most of them look like this. So what are they really? Basically, the most simple form type of capacitor is what we call a parallel plate capacitor. So what it's made of is it's very simple. You have a wire here. So the line here, the black line, and here are wires. So this wire connects to a plate. This is just a conducting plate that has, let's say, a rectangular shape. Okay, so it's just a plate with a certain area A, and then you have below that there's a second plate parallel to the first one. So that's why it's called a parallel plate capacitor. You have this other plate here, and between them there's what we call a dielectric. Now, for now, a dielectric, just think of that as it's just a certain material that is not conducting. There's different types of dielectric that are used, but for now, you can just think of uh, this dielectric here as just being air. Air can be used as a dielectric. So if you just have air here, it just means that you have a gap there, just filled with air. The key point here is that when you have a capacitor, the two plates here do not touch directly. There's a gap between them, and the gap is filled with something that does not conduct charges, doesn't conduct current. So current cannot flow across the gap. Charges cannot jump from one plate to the other plate. Okay, that's the key point. So the two plates of the capacitor are not touching, so there can be no current in between here. Okay, uh, that's just one form. That's the simplest type of capacitor. There's also what are called a coaxial cable. This is, let's say, if you have cable TV at home, you use a coax cable. In that case, what you have is that you have like a small cylinder here that is conducting. You have charges that can accumulate on this cylinder here, and then you have an outer cylinder, hollow cylinder here, that is not touching directly the first cylinder. They're separated by air or something else. So this is, in that case, you can put charges on the inner cylinder and charge on the outer cylinder, but charges cannot jump across the two cylinders here. And this is the form of capacitor. But for us, we'll focus on this form here because that's much simpler to work with and to visualize. So this is the simplest type of capacitor. Okay, well, before we learn about what they're used for, we'll understand the basic, we need to understand the basic property of capacitors. So the first thing you can do, the simplest thing you can think about doing with capacitors is, let's say you have a capacitor, the first thing you can do is just to plug it to a battery, connect the battery to the two plates. So let's say you have this battery here which has a voltage of 0.76 volt. This is just a random value like this. And let's say that the positive terminal of the battery is here and the negative terminal is here. You connect that to a capacitor here with the positive plate. Let's say you have a plate here and a plate here. Now what will happen? Let's say initially there's no charge on the capacitor. So let's say the capacitor is initially uncharged. You connect to the positive terminal. What happens? The battery will push positive charges this way. So the positive charges will start to accumulate on that plate. These charges cannot move across the dielectric, so they start to accumulate on the plate. They have nowhere else to go, so they will start to pile up on the plate very quickly. So the battery starts trying to keep adding, pushing more and more positive charges, but you know that positive charges repel one another. So very soon you have a lot of positive charges here. the battery is trying to push more charges, but it gets more and more difficult to add charges because there's this large repulsion from the charges already on the plate. So what will happen? The battery for a while will add charges, it gets more and more difficult, so the current will slow down, and eventually you reach a point where there's so much charges there that the battery is not strong enough to add additional charges. So when you reach that point, we say the capacitor is fully charged, and then the current stops completely because the battery is trying to add charges, but there's too much repulsion, so it cannot add any more charges. So we end up after a certain time with what we call a fully charged capacitor, and you have charges here accumulated here, and the current goes to zero. There's no current anymore after a while. And of course, if you have positive charges here, it's because you have moved positive charges away from this plate here. So the bottom plate becomes negatively charged. If you have a total charge of plus Q on the top, you always have the opposite charge on the bottom plate, minus Q. Okay, so that's what happens if you connect a capacitor a battery. You're going to add charges to the plates, and eventually, very soon, the current will stop completely. Now you can say, okay, but what happens if I change the voltage? I go back here, I change the battery. Let's say instead of 0.76 volt, I double the voltage. Let's say I connect to a 1.52 volt battery. What will happen? Then the 1.50 volt battery is stronger. It will be able to add more charges. So the total charge here that's on the positive plate will get bigger if you double the voltage. But it turns out that if you double the voltage of the battery, the total charge on the positive plate here will double also. So if you triple the voltage, you're going to triple the voltage on the top plate. And every time you have a certain charge on the top plate, you have exactly minus that charge on the bottom plate. But the key point is that the charge that you have on each plate is proportional to the voltage. You double the voltage, you double the charge. Triple the voltage, triple the charge. So we can summarize that into a very simple equation. So here I'm just mentioning that again. The charge Q on the positive plate is proportional to the voltage applied to the capacitor, and the charge on the negative plate is just minus Q. So that gives us a very simple equation, and this is a very key equation for capacitor. You're going to be using that equation again and again for quite a while. The charge in this equation, Q, is the charge on the positive plate. Okay, so the charge on the positive plate is proportional, it's a constant times the voltage applied to the capacitor. Okay, I want to insist, this C here has nothing to do with the unit Coulomb. It's not for Coulomb, it's a new parameter, a new property of circuits. So it's unfortunate that we use capital C for the unit Coulomb, but usually it's clear what we mean by, from the context you can tell if it's a unit Coulomb or something else. This C here is a property of your capacitor. If you change the capacitor, you get a different value of C. So this C tells us how much charge you have on the positive plate if you apply a certain voltage to that capacitor. Okay, and the charge on the negative plate is just minus Q. So this C is a property of the capacitor, and that's what we call the capacitance of a capacitor. Okay, it's a bit confusing at first, but just think of a resistor. A resistor is an actual object. It's the thing you connect in your circuit. Then for a resistor has a property that we call the resistance of that resistor, right, in ohms. So a resistor is the object, resistance is the property of the resistor. Now, for a capacitor is the actual object, but a capacitor has a property that we call is capacitance, and that's what we call C. Okay, that's the capacitance of the capacitor, like the resistance of a resistor. And what it's used for, this capacitance, for a given capacitor, this capacitance will tell us how much charge you get on the positive plate if you apply a certain voltage to the capacitor. Okay. Now, from the units here, you can see for this equation to work, Q is in coulombs, delta V is in volts. So for the equation to work, C, the capacitance C, must be in coulomb per volt for the equation to work. Now, we give a special name to that unit. As a coulomb per volt, we define a new unit that we call a farad. So 1 farad is 1 coulomb per volt. And the farad is a unit we use to give the capacitance of a capacitor. That weird term here, that weird word Farad, comes from, you might have guessed it, from a physicist, Michael Faraday, very famous, did a lot of very fundamental work in electricity and magnetism in the 19th century. So he was really one of the key figures of discovery of electromagnetism. So 1 farad is a unit we use for a capacitor. It turns out that almost no capacitor you have in real life has a value of about 1 farad. It's a big unit for capacitance. So often we'll work with capacitance that are fractions of a farad. We can have millifarad or MF, that's 10 to the minus 3 farad, 1,000. But even more frequently, we're going to have a capacitor that have capacitance equal of a few microfarad, mu f, which is a millionth of a farad, 10 minus 6, or even we'll deal with capacitors in nanofarad. A nanofarad is 10 to the minus 9, a billionth of a farad, or even sometimes we'll go to picofarad. Pico stands for 10 to the minus 12. So 1 picofarad is 10 minus 12 farad. Okay, let's do a quick example, very simple example. Let's say you have a capacitor of 3 microfarad and you connect to it a 12-volt battery. Question, what would be the charges on the 2 plates of the capacitor? Well, the charge on the positive plate is given by the equation we saw. It's just Q on the positive plate is C times delta V. This C, again, that's the capacitance of the capacitor. So this C is our 3 microfarad, or 3 times 10 minus 6 farad. Delta V is 12 volts. So you multiply 3 times 10 minus 6 by 12, you get 36 times 10 minus 6. And what you get, the answer would be in Coulomb because you're calculating a charge. So a capacitance times a delta V gives you a charge in Coulomb. So you get 36 times 10 minus 6 Coulomb, which we can write as 36.0 microcoulomb. That's the charge on the positive plate of that capacitor when you apply a 12-volt voltage to it. Notice here, again, a warning. You see this capital C here. In this equation, this capital C stands for capacitance. This capital C in this equation stands for Coulomb. But I know it's annoying, but we're stuck with the convention, the notation that everybody uses. You just have, it should be clear from the context when C is a unit, like the microcoulomb here is a unit of the 36, whereas in the equation Q equals C delta V, C is not a unit, it's a parameter, it's a property of a capacitor. Okay, now this is the charge on the positive plate. What's the charge on the negative plate? Well, it's simply equal to minus the charge on the positive plate. So it would be minus 36.0 microcoulomb. Okay, so this is the simplest type of question involving capacitor. You connect a certain voltage, you have the capacitance, what's the charge? And that's it. You just apply the basic equation Q equals C delta V. Okay? Just a last comment. When we draw a circuit, how do we represent a capacitor? The symbol people use is this. Now, I know it would be it's a bit strange at first. You have a capacitor here, so I'll write C for the fact that it's a capacitance, a capacitor. And the way we draw it is we draw 2 lines that are parallel like this. This is meant to remind us of, let's say, if you have a parallel plate a capacitor, the 2 lines represent the 2 plates like this that you're looking at sideways. But I know you look at that and you say, but isn't that a battery? It looks like a battery, but of course the difference is that when you have a battery, you use 2 lines, 2 parallel lines, but of unequal length, right? And we use the length here to tell us which is positive terminal. This is a positive terminal on this side, and the other one here, the short line, is a negative terminal. So for a battery, we have 2 lines that are of unequal length. For a capacitor, we have 2 lines of equal length. Now, it's usually very clear from the drawing if you have a capacitor or a battery. So in the next video, we're going to start drawing circuits where you have capacitors, resistors, and batteries, and we're going to look at what happens to the current and the charges and so on. So we'll start solving circuits that have, in addition to batteries and resistors, we'll also have capacitors, and we'll learn that shortly. Thank you.